Okay, let's start. Uh, Very good evening to all. This is live discussion session for NPTEL course entitled Basic Thermodynamics, Classical and Statistical Approaches. And this is the live discussion session number 12. And this course has course code as NOC24CY04. Myself, Akash Gutal. I'm a third year PhD student from Department of Chemistry, Indian Institute of Technology, Jodhpur. So this is the last session that we are having for this course. This is entire 12-week course, and this is last 12th session we are doing. And first, we will do a quick revision about all the last 11 weeks what we have done. Uh, a quick revision in from the last entire 11 weeks. So in first week, what we have seen is uh, the basics of thermodynamics. What are the thermodynamic system and variables? The concept of system and the surrounding. And we have seen the isolated, open, and closed system. Three types of classical thermodynamic systems. So we have seen the microscopic and macroscopic variables P, Q, PV. Uh, PQ means the position and momentum, and like that. And PVTM is pressure, volume, temperature, and number. Like these are macroscopic variables. And extensive and intensive properties. Extensive properties which are depend upon the quantity of given system, and intensive properties are those which doesn't depend upon the quantity or the up number of amount of a given system taken. Then we have seen what is the equilibrium, how to define equilibrium, uh, zeroth law of thermodynamics. After that, we have seen ideal gas equation, PV is equal to nRT. Zeroth law of thermodynamics, which we know that this is the most fundamental law in thermodynamics, such that suppose we have system A, which is having thermal equilibrium with system B, the system C, and system B, which is also in thermal equilibrium with system C. Then A and B both are supposed to be in thermal equilibrium. So this is the zeroth law of thermodynamics. Then we have seen several gas laws, Boyle's law, Charles law. We know the Boyle's law, which is uh, and Charles law, which are the proportionality that we have seen for volume and temperature. Uh, with, and we have seen uh, the black body radiation. What is the black body radiation? How we measure the temperature using black body radiation that we have seen using practicals. This we have done in first week. Second week, uh, we move towards the real gas and viral equation. Vreal equation with the we have introduced the Maxwell-Boltzmann distribution, that important distribution that we see in how the velocities of the gas molecules are distributed. And we know the functional form as it is exponential to the uh, proportional to the exponential of the velocity square. Okay, and it is proportional to exponential of 1 by t. So you must uh, remember this. And we also discussed how m by t actually determines this distribution. How to solve this problem related to uh, m by t values, that mass and temperature uh, change. And we have seen the real gases. We defined the compressibility factor. So real gases uh, are deviated from the ideal gases, and the PV is not equal to RT for the real gas. And we have defined how we can introduce one another constant for the given gas, which called as compressibility factor. Not constant in the sense, but it is a uh, it tells us how a given gas is close to the ideal gas. It's not constant, sorry. It is a factor which tells you that the given uh, uh, by seeing that factor Z, we can tell that our gas is showing ideal behavior or not, or it is near to ideal behavior or not. Then we have seen the V real equation, which we derive this compressibility factor in terms of molar volume uh, and pressure. And this we have seen that Z is equal to 1 plus V by V plus C by V square plus higher order terms, where B and C are uh, we have seen the virial coefficients. In case of we can write the same equation in terms of pressure also, where we will we had introduced new coefficients for the next the different equation. So we named as them as B dash and C dash when we consider the pressure to define the virial equation. Then we have seen the second order virial coefficient. Second order virial coefficient, that is B, we have determined. Uh, this is for our discussion session. For discussion uh, reason, we have gave discussed the functional form of B of t, that is the virial coefficient, second order virial coefficient, and how it is dependent on the interparticle potential. And you can see it is 1 minus e raised to 2 pi integration of 0 to infinity and bracket 1 minus e raised to minus uh, u r by kbt into r squared dr. And we have seen how this for real gases, van der Waal gases, what this uh, second order virial equation should be. It is B minus A by RT. You should remember this equation, B minus A by RT for van der Waals equation uh, for the real gases. And we have seen uh, at low temperature A will dominate, and at high temperature B dominate, because when you increase the temperature, the 1 by T factor will reduce the dominance of A from the equation. Okay, so that's why at high temperature B will dominate, and at low temperature, when temperature is very low, so this factor will dominate than the B, and A will be dominating factor at low temperature. Similarly, we have seen what is the real gas equation. In real gas equation, we have defined uh, defined the TB, and which is given as A by BR. Then we have seen heat and work with as a path function. We know we defined it them as path function, which depends upon path. We have introduced what is the specific heat, or we introduced the specific heat with, and then we have introduced the first law of thermodynamics. Specific heat only we have introduced, not specific heat at constant volume and pressure, but the general specific heat. What is the definition of specific heat, or the what we or we can say the heat of the system. So that is the so we have defined what is the definition of this specific heat from the equation of heat. Okay, so we have shown that proportionality of heat change is proportional to m times the change in temperature, and the proportionality constant will naturally comes out to be specific. And then we have discussed just after that the first law of thermodynamics, which tells us that total internal energy change of your given system will be the addition of the heat taken by the system and work done on the system. It's just summation of the both. So it follows the law of conservation of energy, as we know. Then we define what is the total and exact differential. So this is the mathematical form. So total and exact differential. Uh, we have seen that the other factor, suppose f is different upon x and y, and whatever we concluded that the exact differentials are that which uh, the functions for which the path taken doesn't depend, only at the final state and initial state, only that matters for exact differentials. So that we concluded from our discussions of exact concept of total and exact differential. So all state functions are exact differential because they only depend upon initial and the final states of your system. In week 3, so we introduced the work done at the constant temperature. What is the concept of work done in the classical thermodynamics? Just work done, we know that it's just the work done by the gas against the external pressure. And this is we defined as W is equal to minus P external into dV. So this negative sign is actually is because when you consider the work done by the system, it should be negative. And in that case, if work done by the system, we generally consider that the volume of the system increases. And if we see, and this negative sign will maintain the the work done by the system as a negative and work done on the system as positive. Because when we are doing work done on the system, the volume will decrease and the dV will negative. And once it is a negative, then work will be the positive. So that's why this negative sign is introduced here. Then we have seen the constant temperature quasi-static work, which is we know the isothermal reversible work. So minus nRT ln V2 by V1. If you put log here, we can multiply by 2.303 nRT ln log V2 by V1 to the base 10. Heat we already defined in previous lecture that it is a path function, and we have defined it in terms of specific heat. Change in the internal energy at constant volume. Here we introduced that CV, which is true for all gases. CV, that is CV is a heat, specific heat at constant volume. Then we move towards definition of enthalpy. What is the enthalpy? Enthalpy is nothing but heat content of the system, which is the summation of internal energy plus PV state of given system. And delta H we defined it is Cp dt. And Cp here we introduced what is Cp. Cp is nothing but the specific heat of a given system at constant pressure. And we know we actually given the exact we had discussed exact functional form of Cp minus Cv, and from that we derive what Cp minus Cv for ideal gas should be. It is N into R, the number of moles of ideal gas into the universal gas constant. Then we move towards Joule's free expansion. Joule's free expansion, we define what is the Joule's coefficient in J, del T by del V. And you should remember Cp minus Cv del V, del U by del V At constant temperature, we have taken from a relation which we now currently using in this week and the previous week. So you should understand the connection between them, because at that time we didn't define it, and we just directly used in our equations that functional form, and we just derived the Cp minus Cv is equal to R and other equations, that mu and Joule-Thomson coefficient and other equations. But you should understand the connection between them, that the two things, and you must go backward and check that derivation again to understand the derivation properly. And we have seen and let's come to the whatever we were discussing right now about the Joule's free expansion uh, and Joule-Thomson effect. We define isothermic JT coefficient, Joule-Thomson coefficient, mu T, del H by del P, and we also defined that del T by del P as constant enthalpy, which is mu. And mu T is actually exothermal Joule-Thomson coefficient. And the relation between mu T and mu is given here. You must remember this, it's very important. And mu is actually del T by del P, constant enthalpy is equal to minus 1 by Cp del H by del P, constant temperature. And mu is equal to 0 at ideal gas, for ideal gas, because del T by del P and at constant enthalpy process should be 0 in case of ideal gas. And for real gas, we have seen this equation I was telling you, that del U by del V at constant temperature T is equal to del T into del P by del T minus P. So this we have used from the using that Maxwell's relations and Legendre transforms. And you should connect these to two things and then derive this equation again. And we have seen for real gas, van der Waals gas, mu is minus B by Cp, mu is less than 0, del T by del P is less than 0, or it's negative. As you increase the pressure, temperature will decrease. Or and increase the pressure, increase the temperature, pressure will decrease. Vice versa, because they are inversely proportional. And A is equal to 0 for van der Waals gas. Yes. Then we discussed adiabatic reversible work, and these three relations, that PV raised to gamma is equal to constant, TV raised to gamma minus 1 is equal to constant, PT raised to gamma upon 1 minus gamma is constant. And the long expression for adiabatic work done, is simply can be written as CV into T2 minus T1. And this is the uh, expression for work done in adiabatic process in terms of pressure, final pressure, initial pressure, and initial volume and final volume. Then I defined one isothermal compressibility factor, that extra thing, uh, because we used this isothermal compressibility and isobaric thermal expansivity alpha in our uh, problems. So that's why I already defined here in third or fourth, I think third lecture, uh, third discussion session. And this is also currently we are studying this as thermal compressibility and isobaric thermal expansivity. And internal pressure, you must uh, remember this, that's del U by del V at constant temperature is internal pressure. So please understand why we call this internal pressure is because in thermodynamics you can understand this fact, uh, what we can say differential by their units also. By just you see, it is having unit of pressure. Because it is having unit of pressure, and the only heat is related to internal energy, we termed it as internal pressure. Then in week 4, we have seen that heat measured at constant pressure, that is enthalpy. Again, we discuss the enthalpy. So we define that one can only measure the change in enthalpy, not the enthalpy itself, because enthalpy is just internal energy plus PV. So it is very difficult to, one can measure PV, it's okay, but we can't measure exact internal energy. Once you can't measure exact internal energy, you can't measure the enthalpy exactly for given system. But you can measure the change in enthalpy, because it will depend upon change in internal energy and change in pressure or volume, the same. So that's why we can only measure the change in enthalpy. We define the what is the reference state, standard state, pure form at 1 bar pressure at specific temperature, which is we defined at the standard state for given element or given compound or given material. And we have defined what is the standard enthalpy change from standard state to the final state, whatever the state may be, whatever the pressure, temperature, and volume. But we reference our system, the initial system as our standard state. And from taking the reference from the standard state, whatever we change in enthalpy we calculate, that change in enthalpy we will call standard enthalpy change. And we define standard enthalpy of formation of element for any element is zero in its natural form. What it may be in gaseous state or N2, H2, or by diatomic form, we will consider it as its standard enthalpy for formation as zero. And we define the changes, vaporization, fusion, sublimation, etc. And we define how to calculate the enthalpy change, standard enthalpy change for these processes. We define the Hess law for constant heat summation. And the statement is enthalpy change of an overall reaction is sum of the standard enthalpies of the individual reactions. And we define the Kirchhoff's law, the difference in molar heat capacities. Sorry, the Kirchhoff's law that we defined is uh, given by this equation. What So whatever the heat enthalpy change, standard enthalpy change at temperature T2, if you want to need to calculate, is you can add the enthalpy change from temperature T1, standard enthalpy change from temperature T1 plus the integration of del RCP, standard specific heat, into dt integrated over T1 to T2. From, let's say, T1 is less than lower or higher, depends. And the difference in molar and CP, del RCP standard we define as difference in the molar heat capacities weighted by stoichiometric coefficients. And we define this del RCP standard as given in the equation, shown in the equation. And we introduced what is the second law of thermodynamics, the entropy of the system. We define the entropy of the system surrounding a system, and we define the entropy of the surrounding, and we got the conclusion that system plus surrounding entropy must always increase. Then we define the most efficient cycle given by the Carnot, which is Carnot cycle. And we have drawn the PV diagram for Carnot cycle, how to define engine efficiency. We also have seen efficiency of Carnot cycle, and this equation efficiency in terms of heat taken from the hot reservoir and heat expelled to the cold reservoir is also we defined, and depends upon the temperature of the hot and cold reservoir. That equation also we derived, and we came to conclusion that one cannot make an engine with efficiency one which can break the second law of thermodynamics if someone does that. And we defined the entropy. This is the most important equation, second law of thermodynamics. Change in heat during reversible process at divided by the temperature. The unit temperature is change in entropy, which is the we defined as the definition of entropy. And the Kelvin Planck law, I will read for you. It's impossible to make a thermal engine that works in a thermodynamic cycle and generate power while it has heat exchange with only one thermal reservoir. So it's just a statement. We can say it's one of the statement of second law of thermodynamics. In week 5, we have seen second law of thermodynamics, which extended towards the concept of entropy, and the same thing we defined what is the entropy, the Carnot cycle, and the efficiency of the Carnot cycle. Clashes statement we have seen that the reversible uh, the flow of heat from cool to hot body this cannot be possible. And we define the spontaneity. In week 6, again we extended our discussion for the entropy, uh, and same uh, we defined the we discussed more about the Carnot cycle. In week 7, statistical mechanics, uh, we have started the basics of the statistical mechanics, and we started going towards the roots of the entropy, what it is, and why this increase in system plus surrounding and entropies are always favorable, that we wanted to answer. For that, we went on discussing the started discussing the microscopics of the given system, and we have seen that every system is left to itself will on the average change towards the condition of maximum probability. That statement is actually same as that of the uh, spontaneity of a given system, and the different arrangement of atoms and molecules we call it them as microstates, and bulk matter we call macrostates. The position which in the example we can give as position and momentum of atoms and molecules, and in bulk matter we say NPT and NVT symbols, etc. So we discussed that entropy is directly proportional to the microstates. But to make the entropy as additive property, we need to make this W as logarithm of 1W. And because of that, it will become additive. The entropy will become additive. And we got this famous Boltzmann's equation for entropy that S is equal to KB ln W. Ln is actually natural log. And we have seen that this W is power to the 10 to the power 2335, like this, a big number. So we define the entropy in such a way that is feasible to, we can calculate, and it should be, and most importantly, it follows this additive property. Because of that, we defined it as log, the natural log of uh, microstates, number of microstates. And then we discussed the basics of probability. What is the permutation, combination, addition, add, and an or probability. So x and y, if conditions are there, we need to calculate the probability for these two. Then for this, we need to multiply the probabilities for px and py. And if we are using or substitute for calculating the probability, then the probabilities of px and py are added. And we defined what is permutation and combination, which is just mathematical forms. And concept of microstates, most probable state would be that state which having maximum number of microstates. In VCAT, we define what is the most probable distribution, what we can calculate, how we can calculate it. For two level system, the equation for, and we have defined the equation of W, the microstates, for n number of particles, n number of indistinguishable particles with R levels, let's say. So this is the main equation. So, so we would use it in many places, many problems. And if we are having multiple levels, and how we can calculate the distribution, it's the same thing we have seen. Particles are distinguishable and Box's energies are indistinguishable. In that case, what should be the microstates? Number of possibilities, number of partitions is equal to number of distributions given the total energy and not number of ways of a particle occupies an energy level I is the mathematical form we have seen. Maxwell-Boltzmann distribution, how it comes naturally uh, from this the fraction ni upon n, and we define the Maxwell-Boltzmann distribution, and its constants also we define that b is nothing but 1 by kbt. So how boson, fermions are and classical particles are actually distributed, fractional, they're fractions we define. Uh, and we should remember these equations, these three: Maxwell-Boltzmann distribution, Bose-Einstein distribution, Fermi-Dirac distribution. Maxwell-Boltzmann distributions are for classical particles, and Bose-Einstein distribution are for bosons, and Fermi-Dirac distribution is for fermions. So bosons, as we discussed earlier, are quantum particles which are indistinguishable and they have integer spins. Fermions are indistinguishables, but they have half spin. Fermions have property that they can't occupy one energy level more than two, because of the half spin they have minus or plus half spin, and that only one energy level can occupy only two fermions, not more than two. But in case of boson, this restriction is not there. Bosons can occupy any energy level with any number. Then we defined the concept of partition function here. And you should remember this partition function is very important aspect in statistical thermodynamics. And it relates entirely from classical to statistical part, which is the only thing which relates it is the partition function. Boltzmann distribution, uh, We have seen in terms of partition function, we defined what is the entropy of using the probabilities. This equation S is equal to minus KB summation of Pi into an NPI. And we have defined what is the information entropy, Shannon entropy, which is without KB, we can say that it is Shannon entropy. And this negative sign, this is also called negative entropy. It's also termed as negative entropy. And this negative sign came because the logarithm of a thing which is less than uh, the logarithm of a number which is less than one is naturally is negative, and the entropy cannot be negative. It should be a positive quantity. Because of that, this negative sign must be there to nullify this ln pi negative value. The thermodynamic energy, we have defined what is it is average energy. So if anything anything, so from the classical point of view, everything is average from the statistical point of view. So here the internal energy is average energy, which is EI into energy of each level multiplied by probability of ith level. It's a particle existing at ith. Observable pressure, similarly we can define observable volume, we can define, and the statistical definition of internal energy is the average energy, which is integration of the probability distribution into energy into D. Translation partition function, we defined what should be. It's 2 pi mkbt by h square raised to 1 by 2 for one dimension. For three dimension, it is 3 by 2. And similarly, uh, we have defined it. It should be average E, or the average translational energy is minus 1 by 2 kBT, and average in three dimensions is 3 by 2 kBT, which somewhere, we had seen somewhere in the uh, kinetic theory of gases. In week 10, we defined thermodynamic free energy and lot of things related to exact total differential form, uh, which gives you, and we have defined what is the uh, mu, which is the chemical potential. For multi-component system, this is the equation for chemical potential, change in internal energy by changing in the number of ith component at constant entropy and volume. So that is the definition of uh, chemical potential. And some relations we have seen with, and the last week we have defined the different conditions for spontaneity. So these are the four conditions used for spontaneity. Most frequently used condition is change in Gibbs free energy is negative for spontaneous process. And we have seen that entropy is not alone sufficient to determine the spontaneity. And then we have seen from the Legendre transforms how we can get this du, dh, and dg equations. From that, we defined the Maxwell's relations. We have seen what are the significance of the Maxwell's relations, how the sign and how to write these equations we have seen at last week. Then we have defined important the coefficient of thermal expansion, coefficient of isothermal expansion, and important equations related to Cp and Cv. So this we have seen from last uh, 11th week. And now in the 12th week, we actually this NPTEL lectures are about the solving um, tutorial problems. And the last concluding lecture was there. And current now we will start this week's practice problems. So the first problem is find the incorrect Maxwell relation. So what we there are four relations are given. We need to find out which relation is incorrect. Please take your time and try to calculate it. Like 2 3 minutes. So hint in this question is you start from Legender's form transforms of this all the del U, del H, del N, del G. From there, you try to derive using Maxwell's relations these uh, equalities. So I will write first here the equation of du, TdS, PdV. Then we have H is equal to S plus VdP. G is equal to STT plus VdP. E equal to STT minus VD. The first relation is del 2U by del S del V. So first take this equation. First we need to differentiate with the volume at constant entropy S. And if you differentiate it, what you will get is minus P. And next thing, when you differentiate with the entropy at constant volume, okay, that would be del P by del S. This is the negative sign at constant volume. And now you need to determine what this form we have seen. This we have got from direct differentiation. But in the option it is not given. It is given as del T by del V at constant entropy. But how we can go there? It's just a max using Maxwell's relation. So we have seen how to write if you know left hand side of the Maxwell's relation, right hand side how to write the opposites must be when multiplied should have dimension of energy. So S, which is counterpart, is T. When T and S are multiplied, we will get the dimension of energy. So its counterpart should be del T, and del P, its counter will be del B. How we determine the constant is just opposite of left hand side is S. And because this naturally here is a negative sign is there, and we know in case of we need to understand the relation between the P and S. If they are inversely proportional, then this negative sign is right in for the Maxwell's relation. And this is the correct relation. First one is correct. The second one, similarly, you can do del S and del P. First, differentiate this expression with del P, which will give you volume at constant entropy. And then we differentiate with the entropy at constant pressure. Right? So again, you need to write uh, expression, Maxwell relation. So here, if you increase the volume, entropy will increase. So it is directly proportional. Hence, our relation will not having any negative sign. And again, the counterpart of S is del T, counterpart of V is del P. The constant of velocity is S. Sorry for that. Yeah, S. But it is actually directly given. Sorry about it's directly given. And this is correct relation. This is also correct relation. So this is correct. This is correct. And the third one, you see, oh. So third one, if you want to see is del A by del T del V del to N is nothing but if you differentiate it with del B, it will be minus P. Again, del T will be T minus del P by del T at constant volume. You need to determine. Same use the Maxwell's relation del S by del V, but this is negative. And once it is negative, uh, yeah. So it should be del S by del V, not del S by del T. Okay. So that is the mistake. So this is the wrong relation. This is the incorrect Maxwell's relation. And for practice, let's try del 2 uh, del square G by del T del P. Write it for practice. Del square G by del T by del P. That will give you. So differentiate this first del P, del by del P at constant temperature T will give you volume. And once you differentiate with again with T at constant pressure is del V by del T at constant pressure P. Fine. Now, if you see, try to write its counterpart. Del P. Then if you try to write the counterpart is minus del S by del P at constant temperature. That's the Maxwell relation and it's true. So the wrong relation is third, option number 3. So the next question is Given that alpha is a coefficient of thermal expansion and kappa T is thermal compressibility, then del H by del V at constant temperature should be. Let's try to solve this problem. For your information, I can write here kappa T is minus 1 by V del V by del P at constant temperature T, and alpha is 1 by V del V by del T at constant P. Use the same Legendre's transform. So first try to determine what is del H by del V at constant temperature T. So we know del, so we know del H is equal to TdS minus plus VdP. Hmm. And we differentiate with respect to volume at constant temperature T would be del H by del V at constant temperature T plus V del P by del V at constant temperature T. And so if you see it carefully, here we need to use Maxwell relation, if you understand, because this is entropy and volume, and we need it in uh, volume and temperature, or something, volume and temperature. So how we do it is T into, so let's say del S by del V. The If you see the proportionalities, if volume is increased, then S entropy will also increase. Because of that, this is the positive relation, but in the Maxwell's relation, and V's counter is del P and S is counter del T at constant volume P plus V into del P by del V at constant temperature T. Here del P by del T is there, but we need it with del V by del T. So what we need to do is, so we use the relation that del P by del V at, and let's say by, sorry, del V by del T, and the constants will be del P by del V at constant T, del V by del T at constant P. So using this relation, but we are uh, deriving this relation. So P and V are inversely proportional. And back here, P and T were directly proportional. So PV is equal to nRT. So P and T are directly proportional. We converting this differential into one differential which is inversely proportional and another differential is directly proportional. Because we are breaking that proportionality and we are introducing one inversely proportional differential, we need to introduce negative sign to make overall thing positive. And because of that, this will be T into negative del P by del V at constant temperature T, del V by del T at constant temperature, constant pressure P, plus V del P by del V. So now you just adjust in terms of kappa T and alpha. You can understand it. Del, this is 1 by, you want to give this 1 minus 1 by, uh, minus minus get cancelled. I get 1 by kappa T, 1 by V into kappa T. So T into minus 1 by kappa T V, and this will be into del V by del T is nothing but alpha into V. Also pressure is alpha into V plus this is also 1 by V into kappa T. So alpha V get cancelled, here V get cancelled, and you will get this negative also cancelled, T into 1 by T alpha T into kappa T plus, sorry, it should be okay. Here we just missed. Here must be a negative sign because we are introducing kappa. Kappa T is negative itself. So this with negative will become positive. So that will be negative minus 1 by kappa T. That will give you final answer as if you take out the kappa T into T alpha minus 1. That is our answer. T, T to alpha minus 1 to kappa T. Option number A. So next question is, all thermodynamic potentials are scalar quantities, exact differentials, state functions, all of the above. 1 minute you can take to solve this question. Very simple. And obviously answer must be all of the above because your state thermodynamic potential are scalar quantities. They are not vectors, they are scalars. All thermodynamic quantities are scalars, and these potentials are also scalar because they don't have any directional properties. and their exact differentials. We discussed it. They are state functions. Because of their state functions, they are exact differentials. Both explains each other. The option number two and option number three both explains each other. If they are exact differentials, then they are state functions, and they are state functions, then obviously they are exact differentials. So all three first three options are correct, which means the option number four is all of the above should be correct. Question number four: if the partition function of a given system is 10, then find the Helmholtz free energy of the system. Please try to solve this problem. Very simple. So there is simple equation for the partition Helmholtz free energy F is equal to minus kBT ln Q. This is the simple formula for let's use standard notation. So gives Helmholtz free energy in terms of partition function can be given as minus kBT natural log of partition function. It will give you minus kBT. What is the partition function is? Natural log of 10. And you know what is the natural log of 10 is? 2.303, nothing but 2.3, let's say. So answer should be minus 2.3 k. Option number 3. So the next question. Using the Maxwell's relation, determine a relation for del S by del V, constant temperature T, for a gas whose equation of state is P minus A by V square into V minus P is equal to RT. Four options are given. Please try to solve. Simple. Please work out. Take 3 minutes. So we need to use Maxwell's relation. So if you see the equation, P, so in the form of P, V, and T, but we have given, we need to find out change in uh, entropy uh, per change in volume at constant temperature, which is entropy, which is not given in this equation. So here we can use the Maxwell's relation. So Maxwell's relations are, because of this reason, Maxwell's relations are useful, because we are calculating entropy, the terms related to terms that are having entropy with some measurable quantity, like pressure and temperature. So that is significance of the Maxwell's relation. So here also we have del S by del V at constant temperature T, and we have the relation of Maxwell relation as del T, sorry, del P by del T at constant volume. So immediately we have this functional form, del P by del T, we have this variable in our equation. We can directly derive it. Let's take it in terms of P is equal to, if you rearrange the equation, RT by V minus B plus A by V square. And let's calculate this term, differentiate left and right hand side with temperature T at constant volume. So del P by del T at constant volume would be, this will be constant and it will be 0. And so differentiating with T, this will be R by V minus. That should be your answer. And option number is option number D. The. So next question. If del U by del V at constant T is equal to alpha T minus kappa T into P by kappa T, then evaluate del U by del V at constant T for an ideal gas. It's simple, even it doesn't require any calculation. You can directly give the answer. Think about it for 2 minutes. Even you know the answer, you just work out the problem, the given condition, using the given condition, given constants, what should be the answer? Just try to uh, uh, get the conclusion from the given equation. They are asking internal pressure of the ideal gas. What should be the internal pressure of ideal gas? Its definition is given in terms of alpha and kappa T. That's two coefficients. You just need to find out what is that value for ideal gas. We know the obvious answer is zero. Internal pressure for real gases, ideal gas is zero. And if you want to derive it from the given equation is, so we know the alpha is 1 by V, then V by del T, the constant equation P, and kappa T is minus 1 by V and then V by del P. So you put this equation V by del V at constant T. So alpha is 1 by V, then V by del T constant P into T minus, uh, let's first calculate. Let's first calculate what is the del V by del T in case of ideal gas. We know PV is equal to nRT. So del V by del T will be nR by P. Similarly, del V by del P would be minus nRT by P square. So put in the equation, we will get alpha is equal to 1 by V PV R nR, and kappa T is equal to minus of minus cancel nRT by P square into P. So that will be the answer. You just keep it in the given equation. We'll get del U by del V. So T, the alpha is an R by PV into T minus divided by kappa T minus nR T by P square V into P. PU T is nRT by PV minus nRT by P get cancelled PV by kappa T, which is nothing but 0 by kappa T. Anything 0 by something is, then is 0. So should be option number B. Well, option number 7. Use the relation del U by del V by at constant T is equal to T into del P by del T at constant V minus P. The same relation that we used in uh, back in second or third week. So the same relation to obtain an expression for the internal pressure del U by del V at constant T in terms of P alpha T and kappa T. Try to solve this simple problem. You just need to 2-3 steps work out in your notebook. Just get the answer. So we know that del u by del p will equal to constant t is given to del p by del t at constant minus. So somehow we know alpha and kappa t. They are differentials of involving volume, and we are volume with one is volume and pressure involved, and another is volume and temperature involved. And there are coefficient of expansion, so volume must be there in the equation. But here in right hand side, we have seen that there is a lack of volume term, and we need to introduce it somehow. Because of that, so you need to introduce it somehow. So the way we introduce it mathematically, let's say del P by del V, del V by del T. So this will be having proportionality as a temperature constant, uh, and this will have proportionality as the constant is pressure constant, right? But here to notice, it's a minus P, and here you if you notice del P by del T, P and T are directly proportional, and we are breaking them into P and V, which are actually inversely proportional, and V and T are directly proportional. So we are messing up with the sign, because when V will increase, V will del V will when it is positive, del V will negative, and that will not make this entire the previous equation as positive. To make it positive, we need to introduce negatives, and T negative of del P by del V T del by T. We know alpha is equal to 1 by V, del V by del T, and constant P. Kappa T is nothing but 1 by V minus del V by del P at constant T. And del P by del V is nothing but if you inverse it is minus 1 by KT into V into del V by del T is something of alpha into V minus P minus P, that will give you T minus minus is plus 1 by kappa T, and this V get cancelled, and this will alpha by kappa T, alpha by kappa T minus P. That would be your value by del P, and this, so for that is option number E, alpha by kappa T minus P, option number A. And the next problem is if the equation of state of gas is given by P, Bm minus B is equal to RT, then find the expression for the coefficient of thermal expansion of the gas for the gas. Please do calculate. So we have P into Vm minus B by RT is equal to RT. The coefficient of thermal expansion of gas. The coefficient of thermal expansion is nothing but alpha. uh, 1 by V del V by del T. That will be what the gas. If you do it, that will be Vm minus P equal to RT by P, and Vm is equal to RT by P minus P. To differentiate with del Vm by del T, constant P will be R by P, and if you do it, uh, I need it in this form, 1 by V will be V, and this is our alpha, R by PV. So it's nothing but VV is RT is what it should be 1 by T, because it resembles to the ideal gas equation. For ideal gas also, this alpha is 1 by T, but here the options are different. Uh, and we ask for coefficient of thermal expansion. Coefficient of thermal expansion is del V by del T itself. That's alpha itself. I don't know why it is not. It should be, let's make one option. Should be 1 by T. Be 1 by T. Same as the ideal gas. Is the next equation. Question. Calculate the Helmholtz free energy using the Legendre's transformation if the internal energy is given as U is equal to 4s square minus 2v cube minus 10. So please try to solve this question. I will give a hint for this question. It's not hint. This question is having some problem with it. You just don't calculate it. You just find out what is the problem associated with the question. It's a wrong question. It's a wrong question. So why it is, you just find it out. Just try to find it out why it is wrong question. I don't know how the answer is given. It's one of the four, but I don't know why this question someone get answer. It's fundamentally wrong. And we have seen the Lysander's transform for internal energy as del U by del S at constant V and N into S. And that gave us U minus TS as a definition of Helmholtz free energy. But here, if you see the U, Even if you calculate del u, it will not. The basic problem about this question is this equation. This doesn't follow the the unit of left hand side is not equal to the right hand side, and energy unit is not followed. The If you do the unit analysis, entropy square it is there, totally wrong, and volume cube is there. So they are not following the rules. So some absurdity is there in question. Internal energy cannot be expressed in the form of entropy square minus 2 volume cube because uh, the units are not matching. It should be this right hand side should have unit of energy. Left hand side is internal energy. So that's why this problem has some absurdity. So you should just remember this. This is the form that we discussed as Legendre's transformation. We derived the uh, Helmholtz free energy for classical systems using this Legendre's transformation. The next question, the last question is the Joule coefficient is defined by del T by del V at constant internal energy is equal to 1 by CV P minus T by del P by del T at constant volume. Calculate the Joule coefficient for an ideal gas. This is also well known to you because we have studied Joule coefficients for ideal and real gases. What should be the answer? Just one word answer can give, or for that matter, you can just calculate also. Even if you can calculate the value of del P by del T, then also you will get to know what should be the answer. Okay, we know by previous classes that Joule coefficient for an ideal gas is 0. We need to prove it by the given Joule coefficient equation. Let's say del T by del V at constant internal energy is 1 by CV into P minus T del P by del T at constant V. So let's calculate, just calculate this fraction because this is just constant and your answer will be depend upon this fraction. So it's P minus T del P by del T at constant V. So we know for ideal gas PV is equal to nRT. We need to calculate del P by del T at constant V. So del P by del T at constant V would be nR by V. So that would be so P minus, so this will be P minus T into nR by V. So that resembles P minus nRT by V. So what is the nRT? nRT is nothing but a PV. So if you put the PV, you will get P minus PV by V, which we will get cancelled, and we will get absolute zero answer. So option number A must be your answer. So thank you very much. This is last 12th week and 12th problem solving session. And I don't know, after this, we will be having, I think one interaction session is there. So at that time, we will meet. Uh, and now we are having nearly 20 minutes. So I will be here. If you're having any doubts, you can ask. And if you want to do some discussion also, you feel free to discuss. Uh, I will be here till 9 p.m. And that I don't know when some live interaction session will be there or not, but that will be intimated to you or all through mail. If it is there, then I will also represent in that same. So please ask the query if you are having any. So thank you very much for attending the session. And this is our last interaction or problem solving session. And after that, we will be having exams. So those who are those who are registered for the exam, uh, the best of luck from my side. And again, thank you very much for your attention.